Now let's apply what we've learned about the type 1 and type 2 errors to some new situations and see if we can decipher them. So remember that a type 1 error is when we reject the null hypothesis even though it was true. The type 2 error is when we failed to reject the null hypothesis even though it was false and the alternative was true. We saw that those could have devastating consequences for the legal system. All right, so let's look here. We have a test that's made of sigma equals 0.5 ppms, and sigma is greater than 0.5 ppms. So that's your null and alternative hypothesis. So the true value of sigma is 0.6. Now 0.6 is actually larger than 0.5, which means this part right here actually means that the alternative hypothesis is actually true. All right, so if the alternative hypothesis is true and we rejected the null hypothesis, that means that we made a correct decision. So let's look here. The alternative was true and we rejected the null hypothesis. We're actually in this corner down here. We're making a correct choice. So we can go put that right here. We've made a correct decision. And we can actually write out what that was. And I'll color code it for you to match the table up above. So this was a green decision. It was the bottom right corner. We made the decision to reject the null hypothesis, and that was a good decision. All right, now we're going to do a different test, this time of mu equal to 454 g for grams, and mu not equal to 454. Okay, so the value of mu is 454, and sigma is rejected. Uh-oh. So the true value of mu is 454. So that means that the null hypothesis is actually true because the null hypothesis says that mu is equal to 454, but we rejected it. Okay, so let's go back up and look at the table. The null hypothesis was actually true, but we rejected it. That means that we're making a type 1 error, right? So let's write that out. There. The alternative hypothesis was gone with. The null hypothesis was rejected. But the null hypothesis was actually true. So we should not have supported the alternative like we did. We should have stuck with the null hypothesis. So we made a type 1 error. Oops, type 1. Usually they use the Latin type 1. All right, now I'm going to test a proportion is equal to 20%, the proportion is less than 20%. The true value is p equals 0.17. So that means that the alternative is actually true, but the null hypothesis was not rejected. See, 0.17 is actually less than 20%. So this this alternative hypothesis is actually true. I mean, if you like, you can actually kind of color code for this for yourself. When you say that the sigma is 0.6, you can kind of note, oh, sigma is 0.6 means that this one's actually the true one. Mu equals 454, you can say, well, okay, is 454. That means that the null is actually the true one. So here, when I say it's 0.17, 0.17 is actually less than 20%. So the alternative is actually the true one. Well, if the alternative is the true one, but the null hypothesis was not rejected, let's go back up here and look at the table. So the alternative was true, so we know we're in this column, right? The alternative is true, but we did not reject the null hypothesis. We're doing this aqua error right here, right? All right, so that's what I'll have to type up. And now I'm realizing I probably don't want pink for these because that's too confusing. Those were from the table. I'll make them gray or something to make it more obvious. All right, I'll be right back. And there we have it. We made a type 2 error here. The alternative was actually true, but we failed to reject the null hypothesis. All right, now let's see how this ties into medical testing because, of course, that's very important. So in general, in medicine, when a person walks into the doctor's office, they don't necessarily think they have a particular trait or disease, gluten sensitivity or, HIV or whatever. So we're going to fill out this contingency table for medical testing. We're going to label the errors as either false positives or false negatives. So let's think about it a little bit. When a person walks into the doctor's office, they generally don't think that you have a rare disease. So if the null hypothesis is true, it means they do not have disease. Let's say it's sickness that we're looking for, although you could do it for pretty much any medical thing. I'm going to color this just a little bit, I think, just to make it more obvious. So the null hypothesis in what you assume to be true is that the person doesn't have the disease. The alternative is that they do have the disease. Okay? So all of that comes from the fact that you assume generally that people are mostly pretty healthy when they walk into a doctor's office. I realize that's kind of a weird assumption to make, but even if you want to reverse this, you could change it to the opposite. Okay, so if the null hypothesis is true, and over here, if you do not reject the null hypothesis, you're saying, yep, you don't have the disease. That means that you're testing negative, right? So the test comes back negative. Yep, you don't have the disease. That's what the doctor's office tells you, right? If you make a decision to, if you make a decision to reject the null hypothesis, then you're testing positive. My copy and paste is not working for me. I'm sorry about that. All right, so it's always a little fluky inside a table like this. Okay, so you test negative, you test positive. Okay, so here, the null hypothesis is true. You don't have this rare disease, and the test is negative. So that's a correct decision, right? So correct decision. Patient does not have the disease, and the test is negative. Yay. I mean, that's what we want. We want people to not be told they're sick if they're not. Okay, so let's get the other correct one out of the way. So the other correct one is you do have the disease and you tested positive. So that's another correct decision, right down here in the bottom right corner. You have the disease, patient does have the disease, and test is positive. So they're told they're sick and they actually are sick and they start getting treatment. Very good things to have happen. But there are two other alternatives that we want to pay close attention to. It is possible that you do not have the disease, but the test tells you that you do. This is a type 1 error. So this would be patient does not have the disease, but the test comes back positive. But test is positive. This is a false positive. Right? So a type 1 error is a false positive in medicine. Right? It means that you were not sick with this rare disease or whatever, but the test came back and told you that you were. Now, in general, in medicine, we actually prefer false positives, believe it or not, because then we do more testing, we figure more things out, and we determine whether or not you really have what we thought you had. Right? But that would be not good. Right, to have a false positive because it gets you all worried about something that possibly you don't have. All right, then you have the alternative, which is a type 2 error. So the patient really has the disease, but they're told that they do not have it, but the test is negative. That's not good. That's a false negative. Right? And that's also very bad because, as a matter of fact, in medicine in general, we assume that this is the worst error to get in medicine. And it's because you don't want to have somebody walk out the door thinking they're not sick when they actually are sick. They're not getting treatment. They're possibly getting other people sick. There's contagion factor, et cetera, et cetera, et cetera. So false negatives are really bad. But there's a trade-off. You can't make either one of these turn into zero. Not for a screening test. So you're going to have to deal with the fact that they're both going to occur to some extent. So you can never make them zero, but you want to make them as low as you can. And you also generally want the type 2 error to be lower than the type 1 error. Because keeping somebody with more doctor's visits and more tests, that's fine. But letting them go free when they could get other people sick is generally not fine. Now, also remember that there's some kind of, teeter-totter type of relationship going on here. And you'll also recall that we have some definitions for some of this stuff. Not actually quite what this is, but related. Sensitivity is actually the true positive rate. Called the power of the test, and specificity is the true negative rate. So those two pieces are actually tied into this, and we'll talk about that in the next video because I don't have time, I think, in this one. Actually, I take that back. Let's just go for it. So, sensitivity is the true positive rate. It measures the proportion of people who actually have the disease that are going to correctly test positives. They're the people that actually are sick that are going to test positive, right? And then specificity is the proportion of people who do not have the disease that correctly test negative. Let's recall real quickly here that this value right here is alpha. And the false negative rate, if you recall, is beta. So beta is the false negative rate, alpha is the false positive rate. Oops. All right, so the sensitivity is the true positive rate, the power of the test, the recall. It's the proportion of people who have the disease, that's this group right here, have the disease, that actually correctly test positive. So if you will, it's what proportion is in this group down here, right? So this corner down here will get us your sensitivity, more or less. And this corner up here will get us your specificity, which is your true negative rate. They do not have the disease and they're correctly testing negative. So that's that right there. And also remember always that there's that inverse relationship, that teeter-totter seesaw trade-off between sensitivity and specificity. So we learned that false positive rate is your level of significance, right, which is your alpha. Right? This is your false positives right here. Okay, and that's the Greek letter alpha that we worked with every problem. And I was going crazy when I typed this. This is actually specificity, not sensitivity. Sorry about that. I must have been very tired, right? So the specificity is, let me get that corner for you. Specificity, if you recall, is the probability of testing negative given that you do not have the disease. So if you look back at your table, given that you're in this column that doesn't have the disease, what's the chances you're going to be up in this corner? Well, this bottom portion is alpha, right? So the top portion is 1 minus alpha if you're talking about a conditional probability, which we are. So this would be 1 minus alpha is your specificity. Sorry, that was a typo. So that's specificity. This down here is sensitivity. So that was my typo. I'm sorry about that. Sensitivity, right, which is the blue one as we highlighted earlier on type 1 and type 2 errors. So being over here, making a correct decision. So when you make that correct decision, given that you don't have the disease, you're only talking about this column. Well, the false negatives are up here, and their ratio, their rate is beta. Their probability is beta. So the chances that you're going to make a correct decision is 1 minus beta. So that would be your sensitivity. So let me type that up for you. There. Sensitivity is the probability of correctly testing positive. I should have put the word correctly in there. Correctly testing positive given that you do have the disease. And that would be 1 minus beta. So given that you're in this column, you do have the disease, what are the chances that you actually test positive? Well, beta is the chances of testing negative given that you have the disease. So it's 1 minus beta. Now remember that the two of them are on that teeter-totter together, so you can't set them, either one of them, to 0, because if you did, you would raise the other one unnaturally high. Also, it implies that you're 100% sure of something, and that's kind of impossible. We're not 100% sure when we get a test back that it's positive, and it's positive that we have the disease, or if it's negative that we don't have the disease, right? We just are mostly sure. So I've drawn a little diagram for you to be able to see this. So alpha and beta are on a teeter-totter together. They're on a seesaw together, right? A level, a balance, right? So that means that when one goes up, if alpha was to go down, beta would go up. Now, it wouldn't necessarily go to 100% because, of course, you still can make correct decisions, but it will increase that beta and vice versa. If beta goes down, then alpha will go way up, right? Neither one of those is a good thing. You don't want your false positives and false negatives to go out of control. Also, what I said before, if we had alpha being 0, it would imply that we're 100% sure, and we're never 100% sure of anything, right? We just have evidence to reject H0 or not reject H0. That's all we've got, right? And we can't claim that we have more than that. Okay, last but not least, just a little quick question about alpha. and beta, actually. So Charlie's going to perform a test at the alpha equals 0.05 level of significance. Felice will perform it at the 0.01 levels of significance. If H naught is true, who has the greater chance of making a type 1 error? Okay, a type 1 error is measured by alpha, right? So that would be Charlie, because Charlie has a higher alpha rate. Done, right? He has a higher chance of making that type 1 error because he has the larger alpha value. Now, if H naught is false, who's got a higher chance of making a type 2 error? Well, I'm going to bet that's Felice, but let's see why. So Felice has a lower alpha. That generally means that her beta is going to be higher, right? So she's going to have a higher beta than Charlie. Therefore, she is more likely to make the type 2 error. Right? It's that teeter-totter relationship. Charlie has a lower alpha, so a lower chance of making a type 1 error, right? But that means Felice will have, oh, excuse me, Charlie has a higher alpha. Let me reiterate. A higher alpha, so he has a higher chance of making type 1, but that means he has a lower chance of making a type 2, right? Felice has a lower chance of making a type 1, therefore she has a higher chance of making a type 2. There, I just wrote that a different way just to make sure. So Charlie has a lower type 2 error and a higher type 1 error, right? Felice has a lower type 1 error because her alpha is lower, but therefore she has a higher type 2 error because if her alpha is lower, her beta is going to be higher.